fellow naval architects, ladies and gentlemen. My name is Lindroth and I work for NAPA in Finland. Today I will give an introduction on the second generation intact stability criteria. I do not intend to go into the mathematics behind the calculations, but instead provide an overview what this all is about, how we got to where we are now, and what this now all means. Before we begin, please note that the views expressed here are my own and do not necessarily reflect the views of others, my company, or other organizations. Here's an overview of the contents in this presentation. I'll start with the evolution and how we got to where we are now, and the main ideas behind the first generation intact stability criteria. Then I'll present the 5 failure modes of the second generation intact stability criteria and the idea of judging these in levels. Following this, I'll present the current status in IMO, mention about limiting values for the second generation intact stability criteria, and discuss some ideas for avoiding vulnerability to finally conclude at the end. So how did we get here? Looking throughout the history of stability requirements for ships, we can note that many of the advancements have been accident-driven. It is quite typical that when something goes wrong, we want to learn from it and try to prevent it from happening again in the future. Another approach is to try to prevent accidents in advance before they happen. This is done, for example, through research or other activities where potential accidents are anticipated and safeguards for these are constructed in advance. Below, you can see a list of a few intact stability accidents in recent history, but also on the damage stability side we have famous accidents that have driven stability legislation forward, like the Estonia or Titanic. The first internationally agreed stability requirements were actually for damage stability. Following the Titanic accident in 1912, the first SOLAS convention was held in 1914 and floodable length requirements were agreed upon. Unfortunately, the first SOLAS was never ratified as the process was interrupted by the First World War. There was actually a maritime conference held in 1889 before the first SOLAS convention, where an attempt was made to introduce international damage stability requirements, but an agreement was not reached and thus no requirements were introduced. The second SOLAS convention was then held in 1929, but did not significantly add requirements compared to the first SOLAS regarding stability. The third SOLAS convention was held in 1948 and introduced the first damage stability criteria in addition to the floodable length requirement. What about the intact stability side then? Well, in 1939, a Finnish fellow called Jaakko Rahola got his doctoral thesis accepted at the Technical University of Finland. The work was titled The Judging of the Stability of Ships and the Determination of the Minimum Amount of Stability, especially considering the vessels navigating Finnish waters. And he introduced 2 curves from where to measure the stability from. The upper one, or the righting lever arm curve, and the lower, or dynamic stability curve. This eventually led to the IMO Resolution A167 from 1968 titled Recommendation on Intact Stability for Passenger and Cargo Ships under 100 meters in length. The resolution, however, recognized that the presented stability criteria were not covering all situations, and that some responsibility also lay with the master, as it is stated that compliance with the stability criteria does not ensure immunity against capsizing. Masters should therefore exercise prudence and good seamanship, having regard to the season of the year, weather forecasts, and the navigational zone, and should take the appropriate action as to speed and course warranted by the prevailing circumstances. 17 years later, in 1985, Resolution A562 was adopted. The title to this one was Recommendation on a Severe Wind and Rolling Criterion, Weather Criterion, for the intact stability of passenger and cargo ships of 24 meters in length and over, and it originated from the works of Yamagata and Japanese stability standards. 8 years later, in 1993, these two resolutions, the A167 and A562, were combined into a single intact stability code, Resolution A749, containing recommended criteria. Finally, in 2008, the current IS code was adopted in Resolution MSC 267, containing also mandatory criteria. So it took a time period of more than 60 years to reach from Rahola's doctoral thesis until we got mandatory intact stability criteria generally for ships. But we are not ready yet. The preamble of the 2008 IS code mentioned that IMO will review the code periodically. Some stability-related safety problems have not yet been fully solved, that for example a ship in seaway involve a complex phenomena that has not yet been fully investigated and understood, and that further research is required. Furthermore, Chapter 1.2 in Part A of the IS Code is titled Dynamic Stability Phenomena in Waves, and the text mentions that some ships are more at risk of encountering critical stability situations in waves. Additionally, subchapters to this mention righting lever variation in waves, resonant roll, and maneuvering-related phenomena that are dynamic challenges for ships at sea. So what do we have in the first generation intact stability criteria then? Well, to start with, there are a few assumptions that are good to be aware of. The situation is considered to be static. The stability is measured in a calm sea, apart from the weather criterion perhaps. Liquid surfaces are horizontal. So let's recall what Rahola did in 1939. He proposed to use two different curves for measuring the stability. From these, the GZ or righting lever curve was the first one, and the second one was the integral or the dynamic stability curve. Then, depending on the criterion, we also apply external healing moments, such as for example wind or a turning moment, and so on. Additionally, some of the values measured from the curves are restricted by openings, freeboard immersion, and so on. Here we can see a GZ diagram and some typical values we can obtain from it, like the inclination or heel, the GM, the range of stability, maximum GZ value within this range, angle of immersion for flooding openings. And the area underneath the GZ curve is represented by the green dynamic stability curve, which essentially represents the energy that is accumulated when the ship is heeled to a certain angle. What about the second generation intact stability then? Let's recall Chapter 1.2 in Part A of the current IS Code, where dynamic stability phenomena in waves is mentioned. This is actually what the second generation intact stability is all about. Therefore, the second generation criteria are not here to replace the previous generation ones, but to complement the IS Code and be used as an addition to the already existing criteria. So the first generation criteria that assumed a calm sea are now complemented with criteria for dynamic phenomena in waves. There is also some guidance for the master on how to behave in adverse weather conditions, but these are not design criteria. The guidance in MSc Circular 707 and Circular 1228 that replaced the previous one are guidance for the master to consider at sea when sailing. For the second generation intact stability, 5 different failure modes are considered, and these can generally be grouped into 4 categories. The first category being stability when incapable of navigation. Here we have the dead ship condition, which considers a ship without power that has turned into beam seas very much like the weather criterion used in the IS code today. The second category is dangers due to excessive stability. Here we have the excessive acceleration failure mode, as sometimes too much stability can also pose a danger, when the motions can become so violent that persons on board no longer can stay in certain locations on the ship safely. The third category being stability in waves. Here we have pure loss of stability, which is when a ship on a wave suddenly just loses stability and may capsize. And parametric roll, when a wave encounters with a particular frequency, results in a large roll motion. The fourth category is stability during navigation. Here we have the surf riding and broaching failure mode, when the ship suddenly may end up sideways against the waves after being captured by the wave. And all of these 5 failure modes are then judged in 3 different levels, with possible ways out. This is a quite different approach compared to the first generation intact stability criteria, where we have a more simple pass-fail method of judging. The first of these 5 failure modes is dead ship. Here, the ship has lost power, is freely drifting at the mercy of the environment, and turns into beam seas. The situation is very much similar to the current weather criterion in the IS code, and in fact the check for the first level in this second generation criterion is actually a slightly modified version of the weather criterion from the current IS code. The second generation criterion uses an extended roll period and wave steepness table. The failure mode is however not intended to be applied for ships with an extended low weather deck, as water on the deck may have an impact on the behavior of the ship. Good to note is also that, as the ship is completely without power, no operational guidance or counteractions are possible to get away from this failure mode. The second one of the 5 failure modes is excessive acceleration. An overly stable ship can experience quick rolling motions that create violent transverse accelerations and become dangerous for the people on board. Good to note is that these accelerations also increase with the distance to the waterline, so the higher up on the ship one is, the larger the accelerations will become. Pure loss of stability is for when a ship loses stability when it is passed by a wave from astern. This is a single wave event, and the stability is lost when the ship resides on the wave crest. The closer the ship's speed is to the wave speed, the longer the ship will reside on the wave and be exposed to the reduced stability. This failure mode, as for the dead ship condition, is also not applied to ships with an extended low weather deck. The fourth of the failure modes is parametric roll. Parametric roll is actually a resonance phenomenon. A ship can, if it encounters head sea or following sea waves with a certain frequency, start to roll with its own natural rolling period. The main resonance of this phenomenon occurs when the wave encounter frequency is close to twice that of the natural roll frequency of the ship. And as it is a resonance phenomenon, it has a limited frequency range. An increased roll damping can help reduce the amplitude of parametric roll. The final of the 5 failure modes is surf riding broaching. Of these 2, broaching is the dangerous one, but as surf riding often precedes broaching, this is what the failure mode criterion focuses on and what we want to prevent. Surf riding is when a ship is caught by a wave approaching from the stern that accelerates the ship to the speed of the wave. During this surf ride, the rudder can become ineffective and the ship unstable in yaw, which can lead to broaching. Broaching, on the other hand, is when the ship, due to instability in yaw, experiences an uncontrollable turn that usually leaves the ship beam on to the waves. The resulting roll motion from the turn and facing the waves can also lead to a capsize, endangering the ship, its cargo, and everyone on board. Now when we know what the failure modes are about, it's time to check the mechanism used for judging the second generation intact stability criteria. The new criteria are no longer checked with a simple pass-fail methodology like their predecessors in the first generation criteria, but are now judged in a stepwise manner with 3 steps, and some possible ways out along the way, like operational limitations and operational guidance. The first level for the criteria is a simple check for sensitivity of the failure mode in question. The second level is more complicated and involves probabilities, while the third level is a direct stability assessment involving simulation. From these, levels 1 and 2 can be calculated using an advanced stability software such as NAPA, while level 3 calculations might need to be ordered as a service. This figure is from the interim guidelines for the second generation intact stability and illustrates the level approach for determining if the vessel complies with the criteria with a specific loading condition. The order of which to do these checks is not regulated, but by starting with level 1 and going down the chart, the complexity of the calculations is also increased gradually. If a ship does not pass level 1, it can move on to the next level, 2. If it does not pass level 2, it can move on to the next level, 3, or the direct stability assessment. By, for example, introducing operational limitations, such as limiting the operational area to, say, the Mediterranean, instead of unrestricted service, a ship can also prove compliance with level 2 using the different environmental conditions. And if a ship failed the direct stability assessment, operational guidance could be worked out, allowing it to still operate in the same environment as long as certain measures are taken when the situation needs it. Operational limitations are general restrictions for operation and can be applied with the level 2 assessment. These can, for example, be limitations to the area of operation, the route, or season. Or they could be related to the maximum significant wave height, which then requires a reliable forecast on the weather conditions, and that there is enough time to adjust the route to avoid dangerous conditions in the event of an approaching storm. Operational guidance, on the other hand, follows level 3 calculations and are more detailed instructions on possible actions to take during operation in order to avoid dangerous situations when they arise. Such actions could be to change the speed or heading against the waves. This, however, requires a more detailed forecast. Operational limitations and operational guidance can also coexist, where, for example, operational limitations normally is applied, while operational guidance is used only when wave heights for operational limitations are exceeded. Waves are part of the weather conditions a ship faces at sea. If we recall the statement from Resolution A167, we can see that the conditions the second generation intact stability criterion is intended for are clearly mentioned in the paragraph. It mentions masters should therefore exercise prudence and good seamanship having regard to the season of the year, weather forecasts, navigational zone, take appropriate action as to speed and course warranted by the prevailing circumstances. For waves in the calculation of the second generation intact stability, we therefore use spectral density or wave elevation for the short term and wave scatter table for the long term. With the new second generation intact stability criteria calculations, some additional input is also required. For the first generation intact stability criteria, you typically need a 3D hull form, loading conditions, openings, and so on. While as the second generation intact stability criteria considers dynamic behavior and waves, we also, for example, need the roll period, roll damping, a resistance prediction reaching over the service speed, number of propulsors and their diameters, the thrust curves for the propulsors, wake fraction and thrust deduction factors. Of these, the first two are related to the rolling behavior of the ship, while the rest are for the surf riding calculation. For the wake fraction and thrust deduction factors, there are some simplified formulas that can be used in the explanatory notes. Good to note about the surf riding broaching is that the level 1 check is very simple and considers only the ship length and fruit number, while the level 2 calculation check if the ship can reach the speed of the wave. This speed check, however, needs the resistance and propulsor inputs, which are loading condition dependent and may not easily be available at very early stages of the design. So where are we at the moment with the second generation intact stability in IMO? Well, the work started a long time ago, and it has probably been, if not one of the longest ongoing agenda items at IMO. The development has been conducted by participants from multiple and different organizations. Alternative methods have been discussed along the way, and when the industry got involved, also additional sample ship calculations for different ship types and ships of different size were submitted. The content of the draft regulation was completed in SDC 7 in 2020, and the explanatory notes content was finalized in SDC 8 earlier this year. The explanatory notes is expected to be quite a bulky document consisting of possibly more than 250 pages. So the interim guidelines were approved by MSC 102 in December 2020 and the circular published in early 2021. The explanatory notes were approved by MSC 105 in May this year and will, once they have been edited by the Secretariat at IMO, be circulated, possibly later this year. Good to know is that the second generation intact stability criteria have been published for trial use and that feedback on the use of them has been requested. The criteria are aiming at becoming part of the non-mandatory section in the IS code. The existing weather criterion is essentially the level 1 check for the dead ship, so some solution is still needed here before the new criteria can be included in the IS code, as the weather criterion currently is mandatory. Also, please note that even if the criteria are non-mandatory, they could be required by a flag state administration or through contracts. Then, something about the limiting values for the second generation intact stability criteria. The first generation intact stability criteria normally result in a limiting curve based on draft and GM and possibly different curves for different trims. The second generation intact stability criteria, however, does this differently as the criteria are more complex. Firstly, not all criteria are affected by GM or KG input, like the surf riding and broaching failure mode. We have also one criterion that is negatively affected by an increase in GM or reduced KG, the excessive acceleration. And parametric roll is a resonance phenomenon. To consider all of these, the second generation criteria instead uses matrix calculation, where each draft and GM value pair is calculated separately, thus forming a map where allowed and non-allowed areas can be presented, a matrix. So the matrix calculation can result in a minimum GM limit, like in the first generation criteria, a maximum GM limit due to excessive acceleration, and non-allowed areas due to the resonance phenomenon in parametric roll. So, how can one then safeguard one's designs against these failure modes? Well, one way is to utilize the simple checks in level 1 or the criteria for when a failure mode is considered applicable for a ship. Here, the wind surface area is 1, as it is directly related to the dead ship condition. Speed is another, The Froude number is used for applicability for the pure loss of stability failure mode and as one of the checks for level 1 of the surf riding and broaching failure mode. Length is another, also used in the level 1 check for surf riding and broaching. GM or KG also affects the level 1 checks of all failure modes except surf riding and broaching. Additionally, pure loss of stability has a GM minimum criterion in level 1, and the parametric roll has a GM variation criterion in level 1. Do note with GM and KG that, as I mentioned before, the excessive acceleration failure mode is negatively affected by increasing the GM or decreasing the KG. A too good stability and a short rolling period will result in more violent roll motions at sea. And finally, also the hull shape has an impact on the outcome, as the stability variation when a ship is on a wave or not has an influence on pure loss of stability and parametric roll. Still, perhaps most importantly of all, even if it is not a design criteria, is to have a skilled master and crew and to avoid dangerous situations when possible. So, what does all of this then mean? Firstly, it is important that everyone involved is now also aware of the criteria. This includes designers, the crew on board, class societies, and flag administrations. These new second-generation intact stability criteria may place designers in an uncertain situation. This could be experienced similarly to when the probabilistic damage stability requirements for both cargo and passenger ships were introduced in SOLAS in 2009. Then what about current existing designs? Will they pass or fail these new criteria? Do hull forms need to change as a result of these criteria? Additionally, the crew also likely needs training, as we have differently looking limitation information, and how to interpret this while considering weather forecasts on board the ship. One way of proactively approaching this is to learn by doing, to try out the criteria with current designs and to see if they fulfill the requirements or not. What kind of design changes could improve the situation? And do these require changes to the design process, for example, when considering the required input? As these criteria eventually may go into the IS code, it is better to explore them now and gain the experience needed in advance. The criteria may also need refinement, for example regarding non-standard vessels. And SDC 8 also invited to further study and to submit experience gained on the application of the second generation intact stability criteria. To conclude, the second generation intact stability criteria complements the IS code. It does not replace the existing criteria. The next generation intact stability criteria brings designers something new that previous experience do not necessarily cover. The second generation intact stability criteria is for dynamic behavior or ships in waves and is judged in 3 levels. The second generation intact stability calculations require additional input that may not easily be available at the early design stages. The first 2 levels can be calculated using advanced stability software, and even though the second generation intact stability criteria are non-mandatory, they might be required, for example, in a contract. This concludes my presentation, and I thank you for your interest in the next generation of intact stability criteria.